All right, now 3. So, so we've already talked about 2 things. We've talked about the battery, and the battery provides energy for the circuit. You could use a different kind of power supply, but basically you have something that gives energy to the circuit, and the battery is the easiest thing to talk about. You have some experience with batteries in your life, I assume. Then we talked about the capacitor, which is a little more mysterious, right? So we've talked about the capacitor and it's storing charge and it stores energy. So we have something that provides energy, which is the battery, which would be like a voltaic stack. Something that stores charge, that would be a capacitor, and that would be like a Leyden jar. A Leyden jar was just a giant capacitor. They didn't know it was a capacitor at that point, but that's all it was, is you used the triple electric effect and you stored up charge in that capacitor, and then you could use it later. That's why they had the batteries, and usually those battery cells were all in parallel. Like we talked about later, that allowed you to do the same amount of work for a longer period rather than more work for the same period. And finally, we have the resistor, and the resistor is how we're going to lose energy in these simple DC circuits. So we've already talked a little bit about resistors, but the resistor, which is going to be a little sort of sawtooth wave thing like this, right? And that thing is going to lose energy, Q dot, it's the energy loss, the power, is going to be equal to I squared R. Okay, so the amount of current going through the resistor times the resistance, which we've talked about before, that's how much power you lose. So resistors dissipate energy from the circuit. And basically they do that in the form of heat. So a resistor that you're very used to that dissipates energy from a circuit is your burner on your oven top, right? That's a very high resistance resistor. And there's a coating on it so you don't electrocute yourself, but there's a lot of power going through that resistor, a lot of current going through that resistor. It has a high resistance as well, and that dissipates as power, as heat, and that means you can cook your food electrically, right? I mean, obviously you could have a gas range, I don't know, and an induction range, it's a little bit different. It should be for, that's from your circuit. Okay, so this is the power loss. This is, that's heat per unit time. And this is your current. Not enough room. And this is your resistance. Okay. And I know you can't see the E because it's behind the board. So we do the same thing that we did in the previous 2 examples. First one is what happens in series. Well, basically, if you dissipate energy from one, right, R1, the same amount of current that's coming here is still over here, the same current coming in and coming out. And so the same amount of current goes through here, right? All the electrons that go in have to be pushed out of the resistor, so you have the same amount of current. And the same thing happens here, so I there. So basically you have I squared R1 plus I squared R2, right? So in effect, your equivalent resistance is just the sum of these 2 things. So each resistor independently loses as much energy as it was going to do before. So basically you sum resistances. In B, we have parallel. And we reduce the resistance in this case. That's because the electrons are free to go through the channel, right? If we have this is our R1 channel, your electron can choose to go through this channel or can choose to flow through this channel, R2. And whichever one is going to dissipate more power at the time based on the number of electrons going through it, the electron will go through the other one. But that will make this guy, so if R1 had too many electrons and R2 didn't have enough, so the electron will go through this one to dissipate through here, lose less energy. But that would mean that the amount of energy in this one would increase. And so with all these electrons, with the number of electrons that are going through, which is large, very large, right? It's trillions of electrons, quadrillions of electrons, more than that really, then what's going to happen is that these will basically have the same amount of current going, or these will dissipate the same amount of power, and that will basically, like we'll talk about next time, mean that this one and this one will have different currents going through them, okay? And that's going to give you this 1 over R is equal to 1 over R1 plus 1 over R2 dependence, right? So if these two had the same amount of resistance in them, these had the same resistors, then this would be 2R1, so R would be 1/2 of that. So the amount of resistance would be half if these were two that were the same, all right? So because the currents react to how much energy is being lost in each one of those resistors, because they want to lose as little energy as possible, that's basically what things do in life, then these two channels equilibrate, so they get more, or have equal amounts of power loss. So this guy has more current if R1 is less than R2 than this one, but they have it in such a way that this this product is equal. Okay, so that's resistances. So that's the basic idea about the equivalent resistances for each one of these three kinds of circuit elements that we're going to use in this class. In the example, okay, again, I'm going to talk about what happens, how to do this for a more complicated situation that includes both a series and a parallel part. And then in the next part, we're going to talk about networks of resistors, so we're going to have resistors that do more complicated things. And then in the final part, what we're going to talk about is dissipation, or we're going to talk about RC circuits where you have capacitors and resistors, and that's going to tell us how capacitors store and lose energy over time. Okay. And that's going to finish up what we're going to do with electric circuits. After that, we'll go to magnetism and then electromagnetism. And somewhere in electromagnetism, we'll probably talk about inductance and RLC circuits, possibly just talk about the inductance. And then we'll go on into optics, and after that we'll be done. Doesn't sound like it's too far away, does it? All right?